So in this video, we're going to talk about the addition of alcohols to carbonyls so that we can form acetals and ketals. So, so in this case, let's say that we have a ketone here, and we would react this with two equivalents of alcohol. So let's do one equivalent at a time. So if we have one alcohol here and we react it in the presence of an acid, we end up forming this here, which let me go ahead and just be consistent and use these as CH3s. So, and you can see that we'll form this alcohol here and an OR group here. So essentially, again, mechanism same as we've been talking about. Alcohol is going to attack, electrons go up, and then a proton transfer. So because this is a ketone, this is what we would call a Hemi Ketal. If it was an aldehyde, then we would call it a Hemi Acetal, right? But this is a Hemi Ketal, meaning half a ketal, because remember I mentioned that we would have to do this with two equivalents. So we would have um, another equivalent here of alcohol and acid, and we would go through the process again, and this time we would end up generating this as our product and water as a byproduct. So, and then this is what we would call a ketal. Again, if it was an aldehyde, if we had started with an aldehyde, then it would be called an acetal. But essentially what we can see here is that what we're doing is we're going to take each one of the alcohols that we've added and we add it to the carbonyl carbon in a nucleophilic attack type of fashion. So let's go ahead and go through that mechanism to make sure that we understand what is going on here. So we're going to do the mechanism. And so we have a mild acid, right? So we have an acid in this. So essentially what we're going to do is, since we have a weak nucleophile and an alcohols are weak nucleophiles, it's not strong enough to attack the carbonyl carbon. So what we need to do is we need to make the carbonyl carbon more electron deficient. And we can do that by protonating it, right? Because if we protonate it, we'll end up with a molecule such as this, right? And by protonating this oxygen, by protonating that, what we've done is we've made this carbonyl carbon much more electron deficient. And we can show that by drawing a resonance structure, right? When we draw this resonance structure, we can see that we have made that carbonyl carbon much more electron deficient. So at this point, what can happen is the weak nucleophile, which is the alcohol, is now strong enough to come and do a nucleophilic attack. So it can attack the carbocation, and we end up with this here. Right? So there we go. And then we can get the conjugate base is going to come and deprotonate so that we can get to our Hemi Ketal. So we end up with this. All right. So we've added one alcohol across the carbonyl, right? But remember we said we're using two equivalents of alcohol here to do this, right? So two equivalents. So with that said, then we're going to do this again, right? But now we've regenerated our acid in this step. So we have our acid now. So imagine we have to get rid of that OH. So what's going to happen? Yes, we have to protonate the oxygen of the OH group in order to turn it into a good leaving group. So we go ahead and do that here. Right? And by protonating that oxygen, we've just turned it into a good leaving group, so it can now leave. So we can kick it off, and we end up forming a carbocation in this case. Now, this carbocation is stable because this is a stabilized carbocation, right? A stable carbocation, and the reason is because of the electron donation of the adjacent oxygen, right? So this can help donate and stabilize that carbocation. So this is going to be very favorable, right? So that's a stabilized carbocation. Now, what we're going to do here is we're going to finish off the mechanism by attacking it with the second equivalent of alcohol. So the alcohol is going to come and attack that carbon, and we essentially have this here, right? And then our final step here, one more time, the conjugate base will come and deprotonate to get us back and form our ketal. Right, so this is our ketal. So this is the mechanism of this reaction. You'll notice that it follows a lot of the same trends as the enamine and the imine type of formation. And then in the process, we also lost water right here, right? So we lost water, so that's why water is a byproduct. So this follows a lot of the enamine and imine formation and the fact that this reaction is reversible. So again, you should know this reaction backwards, forwards, and in your sleep, especially when it comes to that mechanism. And another thing is, okay, since we are eliminating water and water is a byproduct, much like the imine and enamine formation, a way to maximize product formation is to eliminate water. And we can do that with anhydrous sodium sulfate or a Dean-Stark apparatus to kind of push the equilibrium towards the acetal or ketal formation. And since this is reversible, then you should be able to do the reactions backwards, both finding the products and the mechanisms. So why don't you try these? And then again, if you have problems or if you want me to check your work for you, you can email me and I can see how you did. So why don't we take this problem here? Now we're going to add water. So we realize that we're going to go in the opposite direction. We're in the presence of acid. Give me the product and the mechanism for that. And then try this one too, right? So this is where we still have two alcohols here, but they're kind of tethered to each other. And again, give me the products and the mechanism for these two reactions. And if you think you have it, um, then take a picture and send it to me, and we can see how you did. All right, so let's see what else these are good for. So let's try this. So here's a problem. And let's say that I want to take this and I want to synthesize this, right? I want to synthesize this. So give me a reagent. Give me a reagent that would be able to do this transformation, right? Give me a reagent that would be able to do this transformation. Go ahead and pause the video and pick what you believe the answer to be. All right, so hopefully you realize that there is no answer, right? That there is no reagent that can do this transformation, at least no single reagent that can do this transformation. Some of you might have been thinking lithium aluminum hydride, right? Well, lithium aluminum hydride, remember, will attack all oxygen carbon double bonds, so it would go after this one also. And keep in mind that this oxygen carbon double bond remains intact, so LH wouldn't be able to do that. You say, okay, well, I was thinking sodium borohydride. Well, sodium borohydride only goes after aldehydes and ketones. It does not go after esters. And we need to go after the ester, not the ketone. So that wouldn't work either, right? So what you realize is that the problem is that the more reactive compound right now is the ketone, right? Ketones are more reactive than esters. And so in order to do this, we would have to somehow protect that ketone, but we don't know of any protecting groups that we know how to protect alcohols, but not ketones. Well, actually, you do. ketals, and acetals are protecting groups for aldehydes and ketones, right? So acetals here, so let me put this here. So acetals protect aldehydes, and ketals protect ketones, right? Because remember, a protecting group is something that you can put on, but you can easily take off. And as we mentioned in these problems over here, we know how to take off these ketals and acetals. We simply add acid, right? So a way that you can do this is to imagine doing a protecting group here where we would react this in the presence of an alcohol. And then in this case, instead of using two equivalents of alcohol, we can use one molecule that has two alcohols in it. And we end up forming this. So here's our ketal. This is our protecting group, right? So we just did a protection step. And now that that's protected, now we can do the chemistry, right? We can reduce that ester to an alcohol and use, yes, we could use LAH at this point, right? We can use lithium aluminum hydride, followed by water because our ketone is protected. So we can get to our product like this. And then all we simply have to do is deprotect, and we know how to do that. We just simply add water and acid, right? And we would be able to take off our protecting group, right? So this would be a deprotection step, right? So that's one way around the synthesis, and you should be familiar with that, right? If you're trying to react one side without reacting the other, and happens to be a ketone or an aldehyde, well, ketals and acetals are great protecting groups for that reason. All right, so let's try this one here. Let's try another question here. And let's say that we have this molecule, right? So we have this here, and we're going to react this with another equivalent of alcohol, right? We're going to react this with another equivalent of alcohol. So this right here is a Hemi Acetal. And my question to you is that we have two alcohols here, right? We have this alcohol here, which I will label as OH1. And then we also have this alcohol here, which I will label as alcohol 2. The question is, which one of these alcohols is going to be the one to react in this process? Which one is going to be the one to react in this process? So go ahead and pick. Is it going to be alcohol 1 or is it going to be alcohol 2? All right, hopefully we realize that it's going to be alcohol 1, right? So this is why I hope that you're not memorizing. I hope that you're truly understanding the concepts and understanding the why. The why is always going to be important in organic chemistry, and we want to make sure that we understand why that's the case. And it's going to be alcohol 1 that's going to react here, because when we have our acid, right? So if we have our acid, the first step here is going to be protonation. So we have our acid, we're going to protonate this, and we end up with a product or an intermediate that looks like this. And then by protonating that, we've turned it into a good leaving group, so this can leave. So this intermediate that I'm about to draw should be able to answer the question. Why is it that it was OH1 that reacted and not OH2? And we'll realize that the reason for it is again, why? Because of the stability of the carbocation. This carbocation is stabilized by resonance. So it's a resonance stabilized carbocation, right? The adjacent oxygen can help stabilize it by donating its electron density by resonance. So that is why that is the position that reacts. So ultimately, when we finish the reaction mechanism, the product that we end up generating is going to be with an OCH3 at that position, right? With me. So that's going to be the product we end up generating, because we would see that the alcohol is going to come and attack here. Right, it's going to come and attack here, and then we go through a deprotonation step. To get to our final product, right? So we have here, and then we have our conjugate base that is going to come, take that goes there, and we come to our product here. So, but again, we want to make sure that we appreciate the theory, and the reason again is because the reason why OH1 reacts is because of it's a resonance stabilized carbocation. So let's do this problem at home, and then again, if you want to try it, you can send it to me, and we can see how you did. So let's do a mechanism here. Can you figure out this mechanism? If we were to take this molecule here, and the only thing we're going to react this with is an acid. That's the only thing we're going to react with is an acid, and we would end up with this here, right? So go ahead and give me a mechanism for this reaction right here. And like I said, if you think you got it, you can take a picture of it and then send it to me, and we can see how you did. All right, I hope this helped, and until next time.